What I want to do now is show you how even climate scientists can be quite surprised by what is happening as a result of global warming. And I will try and explain the role of planetary waves and the role of global warming in extreme weather events. And first of all, I want to highlight the fact that the beginning of the 21st century has seen an unprecedented number of extreme weather events, as noted by the World Meteorological Organization, who has got the task of observing worldwide weather. And these are extreme weather events unique in strength and impact, according to this report published in 2011 by the WMO. Now, we also published a paper on that, on a decade of extreme weather events at around about the same time, and looking at the linkages between global warming and extreme weather. You will find that often when there is an extreme weather event, journalists will ring up scientists asking the question, is this extreme weather event caused by global warming? And typically, a scientist will honestly answer what you answer for a single event. We can't really tell. And what the public hears then is no, probably it's not linked to global warming. But it is simply the wrong question that is being asked there, because it is very clear that in a statistical sense, the number of extreme weather events is linked to global warming and clearly increases with global warming. And so one motivation to write this article in Nature Climate Change at the time was to point out the many things that we can positively say about how global warming affects extreme weather events, and try and change the thinking and the way of communicating within the scientific community on this topic. And it was actually when Nature Climate Change had its anniversary issue recently, looking back at some of the most influential articles they published, this was one of the ones that was highlighted. Now, I want to just, I'm not going to show you many photos of shocking extreme weather events, but I just want to highlight one thing here, that is the Russian or European, indeed, heat wave of summer 2010. This satellite image shows the smoke surrounding a large area around Moscow at the time. This heat wave was associated with a major drought, which made the Russian government stop exports of grains because they were worried about the reduced harvests. And there were these many fires, including at this airport shown on this picture here. And not long afterwards, Swiss colleagues published an analysis of European summer temperatures going back to the year 1500, because there are pretty good records that allow you to reconstruct the summer temperatures so far back in time. And this diagram, if you look at the top panel, it shows the warm summers to the right and the cold summers to the left. The temperature axis is the horizontal one, and every line is one summer. And the gray staircase there, this is a histogram. It's a distribution function of how often you experience certain summer temperatures. And of course, it can be fitted nicely with a Gaussian distribution, a normal distribution, that is the heavy black line there. But if you look at what's happened most recently, on the right-hand side of the plot, you see temperatures are really walking out of that Gaussian distribution, and the hottest summers in Europe since 1500 were in that order: 2010, 2003, 2002, 2006, and 2007. Now, I don't think you have to be a professional statistician to recognize that this has nothing to do with a random distribution anymore, but there's something systematic going on there. And indeed, we looked at data. Oh, sorry, before I come to the data from the world, this Russian heat wave in 2010 was linked simultaneously with record-breaking flooding in Pakistan, which is shown here in the satellite picture. What formed there in Pakistan and what normally shouldn't be there is the greatest freshwater lake on Earth, basically as a result of this flooding. And Pakistan is still suffering from the after effects of this massive natural disaster. And the fact that this was happening at the same time as this Russian heat wave, this is not a coincidence. There is a connection between the two, and I'll come back to that later. But first of all, I want to show you that this increase in record-breaking heat is not just in Europe. This is a global phenomenon. We have looked at the global data, global gridded data sets, and looked at how often record-breaking monthly heat is observed there. And we find that on average, this is now 5 times more monthly heat records than you would expect just by chance in an unchanging climate. Of course, in an unchanging climate, just by random weather events, you can also get a new record, but you just get a lot fewer records than what we actually observe. And this actually can be easily explained by just the shift of the distribution function towards warmer temperatures. That explains nicely that 5-fold increase in monthly heat records. And the time series actually is shown in this bottom panel, and you see that this is going up here, and the blue curve shows what you would expect if the distribution of temperatures is simply staying unchanged but shifting towards warmer values as predicted by scenarios of rising global mean temperature. And then, by the year 2040, we will not see 5 times more records than expected by chance, but 12 times more records than expected by chance. And these are always new records that broke the previous records that already kind of set the bar ever higher and higher as the climate warms up. We use records here rather than a fixed temperature threshold because of a very nice mathematical property of these records. You don't need to know the shape of the distribution function in order to predict how many new records will arise. And so this is a pretty robust result because of that. Another way to look at it is the frequency or the percentage of land area that is experiencing exceptionally high temperatures at any given time. And you can look at the percentage of land area that is 1 standard deviation about the average, or 2 standard deviations, or 3 standard deviations. And those are the 3 curves shown here. And if you just look at the 3 standard deviations, these are real extreme heat waves of the kind of heat that has practically never occurred in the reference period between 1950 and 1980 here. But you see after 1980, it's going up, the number, and at some points, especially during the El Nino event 1998, and then again in 2010, more than 5% of the global land area at any given time had temperatures that were 3 standard deviations above the climatological average. And so for any single event like the Russian heat wave or so, you maybe can still say, oh, well, it could just be a freak event, it could just be chance. But if you take in the big picture with all the data from around the globe, you clearly see there is a systematic trend here. And if you continue that, project that into the future and look at the percentage of months that will be 3 standard deviations above the climatological average by the year 2100, then you find, especially in the tropics and subtropics, you will practically permanently have conditions that are way outside anything experienced in between 1950 and 1980 in our reference period. There's a similar development in record-breaking rainfall events. These are daily rainfall records. This is the kind of thing that typically can lead to some local flooding. And if you analyze the precipitation data from around the world, you also see a clear trend of increasing numbers in daily rainfall records. The increase is not nearly as large as for temperature, simply because rainfall is much more variable than, and also it's just daily events, whereas for temperatures we were looking at monthly mean temperatures. They have much less variance than daily rainfall events, and that's why the global warming trend has a much bigger impact there. But even for daily rainfall records, you see a clear increasing trend over the recent decades. Now, as I already alluded to, much of this can be explained by simply shifting the probability distribution of such events towards warmer temperatures. For heat, it's very obvious, and it's shown in this diagram, that what you could call hot weather, like the orange area and this diagram there under the orange curve, for present day, it grows, this area under the red curve, the curve that's shifted towards warmer temperature, grows very much. So the orange area becomes much larger when you shift this curve to the right. And a whole new area, that red area, arises of a kind of really hot, extremely hot temperatures that have practically never been, or really never have been experienced before. That is what we call a thermodynamic effect. That is a very simple physics, nothing fancy, everything just getting warmer. So at the warm extreme, you get much more hot extremes, and you get much fewer cold extremes there. And to some part of the increase in record rainfall events can also be attributed to very simple physics like that, because a warmer atmosphere can hold more moisture. For every degree centigrade of warming, that's 7% more moisture for saturated air, and that is why the opportunity for having extreme rainfall events just goes up when temperature shifts to the warmer end by global warming. But those simple thermodynamic effects are not everything that's going on, and that's the expected part. Now I come to the surprise part of extreme weather events. There are some weird things happening in the atmosphere as well, and that's what we call dynamic effects. And there was a nice article describing this in December 2014 in Scientific American, called "The Jet Stream is Getting Weird" by Jeff Masters, who runs an excellent blog on weather and climate. And what is meant by this? What does he mean by the jet stream getting weird? Now, an example of this is what happened on 20 February 2015. You see here the number of new record temperatures set on that day in the United States, and you see on the western side of the US, there's a whole lot of new heat records were broken on that day for 20 February for this time of year. Whereas on the eastern side of the United States, a lot of cold records were being broken. So how can this be that simultaneously in one continent you get new records on both sides? That is kind of weird, but the explanation is that there was this kind of a shape in the jet stream. The jet stream is basically a current of air in the upper troposphere in the mid-latitudes. That's a subpolar jet. And this very strong wind flow arises on the temperature difference between the the warm subtropics, and the colder polar areas. And such a gradient in temperature tends to support a strong flow, both in the atmosphere, but a similar thing applies also in the oceans. And so if this jet stream is not running basically west to east, but is very wavy, and it throws a big wave here over the continental US, then on the western side here, California, it brings in a lot of warm air from the south, and you see heat records there, whereas on the eastern side, it's bringing down cold air from the Arctic, and that is leading to cold records being broken there. So here's a famous and very nice animation made by NASA of this jet stream. And you see this, what's shown here is the wind velocity in red. And sometimes the jet stream runs pretty well straight from west to east. And sometimes it has these big waves like now. And whenever these waves become very large in the jet stream, that is due to the planetary waves in the atmosphere, then you tend to get extreme weather events on the ground. An example of that was what happened in May 2013 in the region where I live, in Germany. Sorry, that is a little bit of German on this slide, but on the left you see normal months, some kind of randomly picked typical months, July 1980 in this case. And the colors here show the wind in the north-south direction. So the green colors are southward flow and the red colors are northward flow. And if you like, that kind of reflects the north-south meanders of the jet stream. And on the right-hand side, you see May 2013, and you see a very different kind of pattern compared to the one on the left, namely with very strong alternating regions of strong northward or strong southward wind. And that is related to these strong meanders in the jet stream, or what we would call very high planetary wave amplitudes. And it did cause some major extreme weather events. It was record flooding on the Danube River, record flooding then on the Elbe River in Germany because of this very large planetary wave pattern sitting over the country. And it of course depends on where exactly that wave pattern is located, whether you get strong rainfall or whether you get a heat wave with drought. It depends on where you are. That gets me back to this Moscow heat wave 2010 and the Pakistan flooding. They were just two different parts of the same planetary wave pattern that extended a long way, almost around the whole globe. And that is quite characteristic for these events, that it's not a localized pattern, it's a pattern of planetary waves basically circling the entire globe. So here's a few more examples. These are strips, kind of bands of the mid-latitude that extend around the whole planet. And you see some examples, Europe heat wave, August 2003, that heat wave, the Russian one, July 2010. And you see that, for example, for that 2010 thing, you see a big kind of blob above Europe, but you see also high amplitude of this wave in other parts along the latitude circle. And that is quite characteristic. And it got my colleague Vladimir Petukov, who joined us at the Potsdam Institute many years ago, coming from Russia. He's a brilliant atmospheric theoretician. It got him to think about what is behind this. Why do we see these extended wave patterns circling the whole northern hemisphere associated with these extreme weather events? And he looked at the equations of atmospheric dynamics that are well known, and he was able to derive an equation for the amplitude of the planetary waves. That is this term AM on the left. I'm sure you all can read this equation without any trouble. But nevertheless, I'll explain it for the few of you who maybe not. So this AM is the amplitude of the planetary waves, and you can see that in the denominator of this here, you see on the left-hand side the difference between two terms, k squared minus m squared. And when k equals m, this term becomes 0, and then this whole number becomes very large, because the second part in the denominator, that is a friction term, and the friction is relatively small, and it kind of is there to, it prevents the whole thing blowing up to infinity, but it becomes, this amplitude becomes very large when k equals m. And these are wave numbers of the planetary waves is one thing, and the other is the wave number of what drives the planetary waves, the forcing. This is exactly the same situation as in a forced pendulum, or think of your child on a swing. If you kind of push your child on that swing and you do it just in the right frequency, the natural frequency of that swing, then you can make your child swing very strongly. But if you do it in the wrong rhythm, it doesn't work. And the same thing happens here with these planetary waves. If the driving of these waves, what we call the forcing, which is due to the air-sea contrast and due to the temperature difference, the temperature distribution on the ground, if that coincides with the period in which these planetary waves would like to oscillate naturally, then they can grow to a very large amplitude. And the conditions for that is that there is what we call a waveguide that traps these planetary waves. If the planetary waves are not trapped, they will just dissipate towards the pole, or they will dissipate towards the equator. They go off in a north-south direction. But under some special conditions, these waves get trapped between two latitude bands, and then they can't get out. And if then you have the right kind of pattern of forcing, they grow very large. And so that's a typical resonance phenomenon. And we can determine the conditions for that to happen, the things on the right-hand side of this equation, and we can predict how large the amplitude of these waves will grow. And we have analyzed many of these extreme weather events now, and the predictions by these equations of how large the waves should be match pretty well what is actually observed. So another example is this United States heat wave in July 2011. You see the wave pattern on the top there that you've already seen before, and at the middle panel you actually see just a kind of line showing the wind, the mean north and south wind, and you can see it has a pretty regular wave pattern there going all around. And the bottom, you can decompose that wave into different periods. And some of these periods can be amplified by resonance when they just have the right period there. And so the question is, what are these conditions that favor resonance to occur? What sets up this waveguide that traps the wave? And it has to do with the zonally average temperature in the atmosphere. And if you look at the top panel, that is the zonal wind in east-west direction. I don't want to go in too much detail here, but those cases where the resonance conditions are present, those are the cases where there's like a double jet stream. You have two maxima with a minimum in between. It's those months that are encircled in blue here. And this is associated with a kind of funny shoulder in the temperature gradient from the tropics down to the pole. And where there's this kind of funny hump in the temperature profile, those are the months where you have favorable conditions for the planetary waves to grow very large. And another case study that we did that we published earlier this year is for the record-breaking Balkan flooding event in May 2014. This was one of the most serious extreme weather events to hit Serbia. There was 62 millimeters of rain falling in 2 days. It's almost as much as usually falls in the entire month of May, and there were 62 deaths and 2,000 landslides like shown on that picture. And at the bottom you see another view here, these globes of the planetary wave pattern that prevailed at the time, and it's another classic case of a very wavy jet stream, very large amplitude planetary waves. So there have been a number of groups working on this in different institutions. Our British colleagues, Screen and Simmons, a few years ago looked at the question of whether weather extremes are linked to planetary wave amplitudes in a systematic way, not just looking at some anecdotal example, if you like the case studies that I showed here, but they did this, they analyzed systematically all the months for a number of decades, and they developed an objective index for how extreme the weather situation was on the ground. And then they looked at how many of these months with extreme weather, these are the colored ones here, are correlated with large wave amplitudes. And so whenever a month that was pretty extreme in terms of the weather on the ground was linked to large wave amplitudes, you see a kind of orange or red square there. And when it was with below average wave amplitudes, it's a blue square. And you can see that in most cases, you see many more orange and red squares than blue squares. So in most cases, those months that have shown extreme weather were indeed linked with high planetary wave amplitudes. So what that tells us is that Not all of the extreme weather events are caused by high planetary wave amplitudes, but quite a large number of them, most of them in fact are. Now the other question that you can ask is those resonance conditions that I've been talking about that have to do with a large-scale temperature pattern in the atmosphere and the large-scale wind pattern, do they affect planetary wave properties in a systematic and statistically provable way? Again, going beyond just some anecdotal example to a systematic analysis of the full data set that we have available for that. And the answer is yes, the resonance conditions do affect planetary waves in a systematic way. And this diagram, it may be a little bit complicated for lay people, but it shows the probability distribution of planetary waves in terms of both their phase speed, how fast they move forward, and their amplitude. Now, the phase speed of planetary waves, that is typically what you see in terms of low and high pressure systems moving across the Atlantic. They move along, that's the phase speed of these waves. And the amplitude is how, as I said, how strong that north-south wind flow is associated with those. And the red colors show where, in what direction of that diagram the planetary waves move when you have resonance conditions present in the atmosphere. And at least for the wave number 6 and 7, that means kind of 7 full waves up and down going once around the hemisphere. For those wave numbers, you see a very clear increase in the occurrence of high amplitude waves. They are near the top of that diagram. And with very low wave speeds, they are near the zero line on the horizontal axis. And that is a second insidious property of this resonance. It's not just about the wave amplitudes becoming very large, it's about these waves becoming quasi-stationary, so they stop moving. You basically have a high and low pressure system sitting in one spot, not moving away, for sometimes a couple of weeks on end. And that, of course, is what causes the real extreme weather events on the ground. And that was a problem with this Balkan flooding event, for example, that for days on end, that rain system was just sitting there without moving away. And the same thing with the Russian heat wave or the European heat wave 2003. It was a very persistent weather situation. There was simply no low pressure moving in from the Atlantic or so that could have brought relief from that heat wave. And this analysis objectively shows that when you have the resonance conditions in the atmosphere, you do indeed get more likelihood of this kind of high amplitude and quasi-stationary waves in the atmosphere. Now, the final question is, in a way, are things changing? I've described how resonance causes big waves, how big waves cause extreme weather events. But now you ask, does this have anything to do with climate change? Is this changing? And there, again, we have done the analysis. This paper was published in Science last year, demonstrating that indeed there are systematic trends there in the atmosphere. One is that the jet stream is slowing down, which is part of that whole complex of change that leads to more likely persistent high amplitude planetary waves. And it's also shown that the jet stream is systematically becoming more wavy. So we developed an index for how wavy the jet stream is. You can measure that kind of along the path length and compare it to how long a straight jet stream would be, and you can get this curviness index. And the blue and the red showed probability distributions for the curviness index before and after the year 2000. And the one after 2000 is clearly shifted towards the right, so towards higher curviness values. And so we would argue the data show that the jet stream is slowing down and it is getting more wavy. And if you look at how frequently these resonance conditions together with extreme weather events occur, you see that indeed there is a cluster of recent events. These gray bars show a histogram of how often these resonance events happen. It's not very often, They are 4-year periods, and in the past there were typically 1 or 2 of these events in such a 4-year period. But in the recent 4-year periods, there have been more of these events. And we plotted on top of that the temperature anomaly in the Arctic relative to the rest of the northern hemisphere. So that curve shows you the time where Arctic disproportionate warming really took off around the year 2000. And we didn't plot that on there by chance, but because the theory predicts that this should have something to do with Arctic warming, and that the strong Arctic warming actually increases the chance that such resonance events occur. And the reason for that is, if you look again at this diagram that I showed earlier, where I said there is this little hump in the temperature curve, and that really gives you favorable conditions for these waves. Now, if you have the sea ice in the Arctic shrinking, then you get extra warming just in that latitude belt between 60 and 70 north, where formerly you had sea ice cover, and now it's retreating, and you get particularly strong warming there. So that, of course, enhances the chance to get such a hump in that temperature curve, this shoulder that you see there where the arrow is, and that's exactly what leads to the double jet and the conditions for wave trapping in the northern hemisphere mid-latitudes. And yeah, of course, we know that the sea ice cover is shrinking. This is what it looked like in the 1970s. That is what it looked like in 2012. That was thus far the record low. It looks like we may well be beating that record again this year. In the last few months, sea ice cover in the Arctic Ocean has been running record low values once again. And if I look around the room here, I think all the people are young enough that they will probably see this picture when it appears on the cover of some news magazines. We don't know exactly when this will be, but I'd be pretty sure that it will be in my lifetime, unless I get run over by a bus when I walk out here tomorrow. So to conclude, what I think I have shown is that some of the most extreme weather events, record-breaking, high-impact weather events like the European heatwave 2003, I didn't mention that this caused 70,000 fatalities, which was analyzed afterwards in the mortality statistics. Similar death toll for the Russian heatwave 2010 has been estimated. That some of these most extreme weather events have been associated with very high planetary wave amplitudes. We have also shown that these high planetary wave amplitudes, the very strong meanders, are linked to the presence of resonance conditions in the atmosphere. It's a resonance phenomenon, just like with your child on the swing when you push it. And there is some maybe less strong but preliminary evidence that the resonance is becoming more frequent, and this may well have something to do with the disproportionate warming of the Arctic. That is what the theory would suggest. I have to say that this is all fairly new and fairly exciting science, so this is not part of the well-established curriculum of global warming science. It's not as clear as, sea level rise resulting from global warming. It is a cutting-edge research, and in that sense, it's kind of precautionary note. This is not well established, and there will be still there is a lot of work being done on this, and it is a very exciting area to be working on, because we can expect lots of new interesting developments and studies and analysis coming out about this very topic in the next few years. Thank you very much.